Angular momentum. Here we see a car on a circular track. As a car is traveling around this circular track, it has linear momentum, P equaling mv, tangential to the path it travels. In addition, by having an angular speed omega, it has an entirely independent quantity called angular or rotational momentum, symbolized by the letter L, where L is equal to r, the distance from the center of rotation to the car, times p. L is a cross product, r cross p. There are two forms of momentum that this car has. Momentum as the car is moving along the track, and a rotational angular momentum as it's moving along the track. We know that as a force changes the momentum, torque, analogously, changes the motion of rotation. Thus, it changes the angular momentum. So recall that summing up the forces, if there's a net force, it changes the momentum in time. That's our impulse momentum theorem. Net forces change momentum over time. In the same manner, summing up the torques, if there's a net torque changes the angular momentum over time. It's an angular impulse. We know that a net force relates to mass times acceleration. Similarly, a net torque relates to rotational mass, the moment of inertia, the rotational inertia, times the angular acceleration. Just as net force relates to inertia times acceleration, net torque relates to rotational inertia times angular acceleration. Breaking apart what alpha means, a net torque equals the moment of inertia times the change in omega with respect to time. Angular momentum, thus, equals I times omega. Angular momentum is the product of r cross p, as we just learned, and is equal to I times omega. It's a vector product of r cross p, the vector product of the position vector r and the momentum vector p. Thus, angular momentum is also a vector. The direction of angular momentum L is the same direction as omega. Just as p is equal to mv, L is equal to I times omega. Just as p points in the same direction as velocity, p points in the same direction as v, L, angular momentum, points in the same direction as the angular velocity omega. They're related both by inertia, a scalar. We use a right-hand rule to determine the direction of omega and L. Your fingers curl in the direction of rotation, such as in the illustration of a rotating disk. Your right hand, the fingers curl in the direction of the rotating disk, and your thumb points in the direction of omega. Therefore, it also points in the same direction as angular momentum, L. Another right hand rule can tell us the direction of torque. We use our right hand. The palm of our right hand points along the direction of the position vector r. The fingers point or curl in the direction of the applied force. And again, the right hand thumb points out in the direction of torque, as seen in the top illustration. What does a torque do? Torque changes angular momentum. Therefore, torque and change of angular momentum, delta L, have to point in the same direction. That's our second equation. Delta L and torque are vectors that point in the same direction. Time is simply a scalar. Since torque relates to the change in angular momentum, the direction of the torque is the direction that the angular momentum is being changed. The direction something is rotating faster, slower, or changing its rotational direction. Since torque is equal to the vector product of r cross f, therefore, torque is perpendicular to the plane that the vectors r and f are in. You will practice this cross product, these right-hand rules, in the ills. Here we see an ice skater. The ice skater has their hands outward, holding heavy masses in their hands, say 2 heavy balls. But the ice skater is rotating about their central axis. But as the ice skater rotates, it stays in one place, i.e. it rotates about a vertical axis through her center, with her arms outstretched. The ice skater, or the figure skater, she has a moving mass by her rotation, but she's not traveling anywhere. Her center of mass, her center of gravity is not moving anywhere. She as a system has no momentum. She as a system has no translational, linear center of mass, center of gravity, the various names. She has no momentum. She as a system is not moving anywhere. She is simply rotating. So there's no linear momentum. She's not moving in a line, but she is spinning or rotating, so she has angular or rotational momentum. Again, angular momentum is a different form than linear momentum. When she pulls her hands in, a phenomena happens that can't not be described with the ideas of momentum. Pulling her hands in, she rotates even faster. If mass and rotational velocity omega were all that were involved, you would not expect the rotation to change. She doesn't change her mass. She simply just brings the mass closer. But clearly where the mass is in relation to the axis of rotation is important. So the distance that the mass is from the center of rotation is the key factor. That's what changed her omega to become larger as she rotated faster by bringing the masses in. L is equal to I times omega. Angular momentum is equal to rotational inertia times rotational velocity. I, recall, is mass times r squared. If we consider 2 balls held outstretched, then I would be mr squared, the mass of the balls. R would be the distance the balls are, the length of her arms from the center of her rotation, about the central point of her body. So mr squared times omega is what L can also be expressed as. We can write this also as mr times v, because r omega is the tangential velocity v. But mrv is also the same thing as mvr, and mv is p momentum. So L is equal to r times p. So L equals I omega is the same thing as L is equal to r times p, momentum at distance from an axis of rotation. You also will experiment with this phenomenon of bringing the masses closer towards your center as you're rotating on the stools during the lab. So consider the figure skater from the previous example, or the illustration below when a person brings weights in as they're rotating on a stool, as you will do in lab. The rotation omega, the angular velocity, changes by bringing the mass in closer. When you bring the masses in farther away, your value of I is greater and omega is proportionally less. The important idea is that angular momentum is a conserved quantity. So therefore, the changes of I are opposite the changes of omega. Big value of I, correspondingly small value of omega. Decrease in I, corresponding increase in omega. Why is L constant? Well, recall that to have a delta L, a change in angular momentum, you need a torque. A torque is not applied when the person brings their weights from their hands closer to their body and farther from their body. There's no external torque applied. External torques are from external forces. An external force would be somebody else pushing on their hands to make them rotate faster. But there are no external forces. No one is pushing on their hands to make them rotate faster or slower as they bring their hands in and out. So therefore, with no external push or pulls, there are no external torques, and so the angular momentum does not change. It remains a constant. So any change in I by bringing in the weights corresponds to an opposite change in omega, since the product of I times omega is equal to constant L, which does not change because there are no external forces creating no external torques. Let's look at our relationships of our variables so far. We know distance can be related to angular distance, or delta theta, the angle, by the position vector r from the center of curvature sweeping a delta theta along a distance. Tangential velocities can be related to angular velocities omega by a same factor of r, just as acceleration can relate to angular acceleration by a factor of r. We then learned that torque or rotational force relates to the linear force by a factor of r. And now we learn that rotational angular momentum L relates to linear or center of mass momentum P by a factor of r2. So our variables, relationships between our rotational and our linear variables couldn't be simpler. They just all relate to each other by a factor of r. An impulse is a transfer of momentum, a delta P, which is caused by a net force over time. Similarly, an angular impulse, a transfer of angular momentum, delta L, is caused by a torque or rotational force over time. And just as P equals mv, L is equal to I omega. Just as F equals equal to dp dt, rotational force torque is equal to dl dt. And just as F equals ma, torque is equal to I alpha. And we also have our kinematic equations relating velocity and acceleration to distance in rotational and linear form, and they look almost identical. And lastly, kinetic energy is 1/2 mv squared. Re, kinetic energy rotational energy, is 1/2 rotational inertia times rotational velocity, 1/2 I omega squared. Let's discuss some examples involving angular momentum. Here we see in this illustration a huge ball. The dots represent stars and clusters of stars and gas clouds. The clusters of stars and gas clouds are being brought together by their own gravity. They're being pulled in. As they get pulled in closer and closer by the mutual attraction, by the gravitational attraction, they start rotating faster and faster. If the original ball has some rotation in part A, then the ball at the center, the bulge at the center of part C, has a much greater rotation. As the particles come in closer, their rotation increases, their value of omega increases. As they come in closer, the rotational inertia, the moment inertia I, decreases. The distance of all the objects for these masses drops, so I is much less for the central bulge where most of the mass is in part C compared to A. If I is 100 times less, then the rotation is 100 times great for the objects, the stars, in illustration C around the center. But just as the figure skater brings her arms in and out with a constant angular momentum to change rotation, this huge ball of stars, as it contracts, rotates faster about its center and slower about its large arms at the edges. What you're looking at here is a galaxy. As a galaxy forms, the gravitational attraction of all the stars and gas clouds in this huge ball, this protogalaxy, start to rotate faster and faster by their mutual attraction, by their mutual gravity. And most of the stars and gas clouds in the central bulge in part C rotate much faster than originally in part A. But the angular momentum of the galaxy cannot change. Why is the angular momentum constant? Well, just as the figure skater's angular momentum is constant as she brings her arms in and out, because no external forces are creating any external torques by pushing on her, there's nothing pushing or pulling on the galaxy. There may be tugs from other galaxies, but the galaxies are randomly distributed about any galaxy. And so there's no net tug, no net external force not creating any external torques. So without any external torques from the lack of external forces on the galaxy, the angular momentum remains constant. the angular momentum remains constant and most of the mass is a shorter distance from the center in part C, then it rotates faster and faster. And the stars out in the edge of the arms of this galaxy will go farther out. As those masses increase their value of I, their rotation decreases. And it's all balanced to add up to the same total angular momentum that never changes because no external forces there aren't any external torques. Here we see a picture of the Earth scaled to the distance that the Moon is. You can see that the Moon is at an angle above the Earth's equator. We know by forces of attraction that the force of the Moon on the Earth is equal to the force of the Earth on the Moon. They tug on each other equally. They tug on each other by their gravitational attractions. But the tug of the Earth on the Moon is different on the front face of the Moon than the back face of the Moon. The force of gravity from the Earth on the Moon is greater on the front because the distance of the front face of the Moon is closer, so there's more gravitational pull from the Earth on the Moon in the front than on the far side or the back. This causes the center of gravity, the average location of the force of gravity of the Earth on the Moon, to be closer towards the front face. Thus, the center of gravity, the location of the average force of gravity, is closer to the front face of the Moon. It is off-center. So the center of mass of the Moon is not the same location as the center of gravity of the Moon. This causes the Moon to be tugged more at its front, which causes the Moon to have an effect that we can see here in the next picture. Cm stands for center of mass. Cg stands for center of gravity. In this illustration, the Moon is exaggerated, being stretched. Why is the Moon stretched somewhat? Well, the Earth is wider around its equator than between the poles, just as the Moon is wider around its equator than between the poles, for the same reason that the galaxy widens into a disk shape as it pulls itself together by angular momentum. As the Earth is spinning about itself, the Moon is spinning about itself, it widens about its equator and is narrower at its poles by the gravity pulling it in to make it rotate faster and widening itself at the equator. So the center of gravity is offset from the center of mass of the Moon because the force of the Earth on the Moon in the near side is greater than on the far side. So the average force of the Earth on the Moon is not the center of the mass of the Moon. And it's pulling on this sort of fatter shape of the Moon around its equator. It's pulling it off-center. So a force that's applied off the center of rotation creates a torque. So the average force of gravity, the center of gravity, being off-center from the center of mass, is creating a torque. We see this in the other illustration. It's like a person applying a big wrench pulling on the Earth from the Moon, but pulling not at the center of rotation of the Earth, but pulling at the poles, off-center. This creates a torque. So the force of gravity of the Earth on the Moon creates a torque on the Moon. The force of gravity is a distance away from the center of rotation, the center of mass, and a force a distance away from a center of mass at an angle, since the Moon is not at the same plane as the equator, causes a torque. So if the Moon is torqued, it changes the rotation of the Moon. Over the vast ages, over the billions of years of interaction between Earth and Moon, the torque on the Moon from the Earth has slowed down the Moon's rotation so much that the Moon only rotates once around the Earth as it completes one orbit. The Moon rotates about itself in the same period of time it takes the Moon to orbit the Earth. Its rotation is once a month, as its revolution, its period of orbit, is also once a month. The torque from the Earth on the Moon has caused the Moon to slow down so much that the front face of the Moon always faces the Earth. The Moon applies a torque on the Earth too. The force of gravity on the Moon is greater on the side of the Earth facing the Moon, and less so on the side of the Earth, on the opposite side of the Earth from the Moon. So the force of gravity from the moon on the Earth is more so on the front side, which causes the torque of the Earth, which affects slightly the Earth's rotation. This effect on the Earth's rotation from the force of the moon off a distance from the center of the mass of the Earth causes a torque on the Earth. So we see here the force lowercase m, the force of the moon on the Earth, is a distance away from the center of rotation of the Earth. This creates a torque on the Earth. And so what happens when you have a torque on a rotating body? The rotation of the body changes. The daily rotation, the spin of the Earth, wobbles. This is called precession. It's a very slow phenomenon. The Earth wobbles like a top. Over a 26,000 year period, the axis of the Earth, the north-south axis of the Earth, slowly rotates over 26,000 years. You will explore this phenomena in the lab, seeing how a torque can make an object precess or rotate, but the idea is simply a torque relates to a change in angular momentum, and in these cases, the torque on the moon and the torque on the Earth aren't changing the rotational speed of the Earth. It's changing the rotational direction. It's changing delta L in direction, not delta L in magnitude of the Earth. So the Earth slowly wobbles as the delta L is changing direction. This has significance to astrology. 26,000 years means that the 12-month zodiac signs is off by a full month about every 2,000 years. So 26,000 divided by 12 is a little bit over 2,000. So about every 2,000 or every 2 millennia, every 2,000 years, the constellations in the zodiac are shifted one full constellation. There are 12 zodiac signs. So whatever sign you were born under, such as Cancer, or Taurus, or Pisces, you are actually one sign off, since most of astrology was written down and is still being used from over 2,000 years ago during the height of Rome. And since then, the Earth has shifted 1/12 of its way around in its 26,000 year precession period. This also means that our current north-south axis that's pointing towards the North Star Polaris is slowly rotating, so that in 12,000 years, the north-south axis will point towards a different star. It'll point near the star Vega. And over 4,000 years ago, the North Star was not Polaris. The North Star was a star called Thuban during the time of the ancient Egyptians. Our axis slowly wobbles. This phenomenon you will learn about in the lab when you spin a wheel to make a wheel precess. If this wheel is suspended by a rope where the rope is pulling off-center from the spinning wheel, then the wheel will have a precession. Just as the force of the moon on the Earth is off-center from the central axis of the Earth, or the force of the Earth on the moon is off-center from the center of mass, the center of rotation of the moon, creating a torque. Here, a rope pulled off-center from a spinning wheel, the force of the rope as a distance from the wheel creates a torque. So the wheel precesses or rotates about the rope. So rather than the wheel simply falling down, the wheel rotates or precesses about the rope. So the wheel rotates about the string or the rope rather than falls by the nature of changing angular momentum, by the nature of a torque creating a delta L in direction. So if the wheel is rotating in the direction shown, then R cross F, the vector product of R and F, creates a torque as shown, and a wheel spinning in the manner shown creates an L and omega. So the torque is perpendicular to L. That means the delta L, the changed angular momentum, is perpendicular to L. And so that tells the L that's the direction to change in. It tells the L to follow the direction of the torque. Or the axle of the wheel, the direction that L is pointing along, chases or follows the torque, which will always take it around the rope. There's an animation on the web page that you can link to see these vectors in action. Another example of angular momentum. When the helicopter's propellers start spinning faster and faster, the body of the helicopter should rotate the opposite way by conservation of angular momentum. There are no external forces, therefore no external torques on the helicopter, so the angular momentum of the helicopter should be constant. If the angular momentum of the propeller blades increases, then I have to have an opposite opposing angular momentum in the opposite direction. A delta L up would be opposed by a delta L down on the body of the airplane. This does not happen because the propeller blades on the other propeller blades on the tail of the helicopter are spinning, which has angular momentum in a different direction. So I need a torque to change the angular momentum on the tail of the helicopter. This keeps the helicopter stabilized. You can ask your cat to explain angular momentum because they are masters of it. When a kitty cat falls, it always lands on its feet. How does the cat do it? Look at the figures of what the cat is doing. We'll probably need to stare at the illustration, the same figure in the PDF file for a clearer picture. What you see is initially the cat flips, and looking at the front half and the back half of the cat independently, we see that the front half of the cat is rotating to face downward, and the cat slows its rotation, the front half, by bringing its paws out. Bringing its paws out increases I and decreases omega, just as the figure skater stretching her hands outwards decreases the rotation, or the stars going out along the disk of the galaxy slows down, omega slows down the rotation. So the cat slows itself, its front half down, to keep facing downwards and rather than rotating past down. And then it brings its hindquarters in, it brings its back legs and tail in closer to decrease I, so the backside then rotates quicker. Then when its backside is where it wants, it extends out its back legs and its tail to increase I and decrease omega, until the cat is now situated, or it's now in the orientation it wants to be, facing downwards. It did this by changing I and omega while keeping L constant. In a much simpler manner, humans can use angular momentum to vary rotation when diving by bringing their hands and legs in and out, performing gymnastics, or as astronauts do, to zero gravity, and astronauts do to do angular momentum turns when working outside of the space station and the space shuttle. The end.